Okay, class. Your assignment today is to measure the wavelengths of red, green, and violet light. So I've asked these two volunteers to help us out. Luke, let's let you explain, how do you intend to do this?
All right, so here we have our red laser, and it is passing through a diffraction grating, which for our intents is equivalent to a double slit. Now, we're going to shine it through this until it hits the whiteboard, and as you can see, it creates these spots. So we're going to measure the distance from these two spots, and as well as the distance from whiteboard to our diffraction grating, and using a math that we learned in class, we can use this to calculate the wavelength.
Okay, sounds good. Let's give it a shot.
All right. So our first one is already set up here.
Let's do the one on the right also.
Yes.
We'll just average them. Okay, you can turn off the laser now. Oh, wait, but don't move the grating. We need to measure that distance. Can you measure the distance from the grating to the wall first? So that way he can move it if he has to.
So it's about...
Not about. I want 3 sig figs here.
Okay. It is 68.7.
Okay, 68.7. Can you write that down? No, that's not X, that's L. And make sure that's centimeters, which is not a standard physics unit, guys. But that's okay. I trust you can handle that.
This distance here.
Okay, so he's measuring the distance from the center bright spot to the first diffracted bright spot on the left side.
That is 59.3 centimeters.
Okay. And then just to be safe, we're also going to measure it on the right side. So it should be symmetric, but it may not be perfect, if we're not holding the laser at exactly the right angle.
That is going to be 59.5 centimeters.
Okay, so pretty darn good. Okay, so what we'll do is we'll use the average of those two numbers when we do the math. Okay, so you can see that we've got the length, we've got the separation between the center bright spot and the first diffracted bright spot. And now the D value, we're just getting that from the manufacturer. We're just trusting that the manufacturer wasn't lying when he told us that. Okay, so with that information, we should be able to figure out the wavelength of the red light. Okay, what we got next here, Simon?
Blue.
Okay, now the laser,
Violet.
the laser is sold as a blue laser, but in fact, it's really more violet. Okay, so we're going to do the same thing as before, and there's the bright spots. Notice they're a lot closer together. I mean, substantially closer together. And it's the same grating as it was before. And it should be the same distance. If nothing moved, it should be the same distance. I mean, the L should be the same.
The distance this time is going to be 30.3 centimeters.
Okay, so we're putting it in as with blue ink, but it's really more of a violet color.
That's going to be 30.4 centimeters.
Okay, so L is the same as it was before, D is the same as it was before. The only thing that changed is X. From that, you should be able to figure out what is the wavelength of violet light. Okay, now we got to do green. All right, so there's the green laser. There are the green dots. And you'll see that it's kind of in between, right?
This first distance is 41.7.
Okay, 41.7, and those are centimeters, of course. You'll have to convert that into meters.
Now our second distance is 43.5 centimeters.
Okay, so excuse me for a second. All right, so here are the numbers. Hopefully they're all legible. The last ones were 41.7, and I can't quite read the very final one. Can you make that a little more legible? 43.5. Our green, looks like our green pen is running out of ink. Okay, so the numbers that you guys see on the screen right now, that should be all you need. You should now be able to calculate what is the wavelength of the red laser, the blue laser, which is really violet, not really blue, and then the green laser. Okay, and then after you do the calculations, I need you to write it up in a lab report as if you were the ones who gathered the data yourselves. Okay, thanks.